Organic chemistry. Today, let us see something about the classification of organic compounds. Okay. Coming to the branch of chemistry called organic chemistry, which of course is a branch of chemistry which deals with the study of compounds of carbon. The organic chemistry is a branch of chemistry which deals with the study of carbon compounds. That is why I've specially mentioned carbon. And you know, this of course is your benzene, which is the parent aromatic compound. Of course, a very important compound of organic substances. Now, a question immediately arises of why the compounds of carbon are studied under a separate heading. Because it is one among the 118 elements that we have in our periodic table, right? But still, the compounds of carbon are studied under a separate heading. It is because of the peculiar or the special properties of carbon. Let's see them. The compounds of carbon are studied under a separate heading because of the peculiar properties of carbon. Okay. What are the peculiar properties of carbon? Let's see them one by one. You know, the most important is catenation. See, catenation is nothing but self-linkage of identical atoms. Simply speaking, see, the carbon atoms can self-link to form chains of a different length and even different shapes also, like this. This is what I call catenation, nothing but the self-linkage of identical atoms. But why carbon atoms form these kind of chains or these kind of cyclic compounds or ring chain compounds or the straight chain compound? You know, the element with the maximum catenation is carbon. Means it is the one which can form linkages to the maximum number. Then of course we have next is a silicon. Of course then comes the sulfur and all. But why is the catenation of carbon maximum. In general, these kind of bonds are formed in a large number. Like that, you can just go on. But why? Remember, if one bond is strong enough, then one more such bond is formed. Even after forming bond with this, also it is a strong one. Then one more such bond is formed. One more, one more, one more. So this way it goes on, because the bond, whatever forms, is a strong one. It is not a weak one. So as long as such bonds can be formed, you can just go on. That is what we call catenation. And the maximum catenation power of carbon is due to its high bond energy. Because the bond energy of a particular bond formed between the carbon atoms is more, such bonds are formed in large number. When I say high bond energy, it is difficult to break the bond. When I say it is difficult to break the bond is a stable one. And when I say that the bond is a stable one, what is the problem in forming such bonds in a large number? We don't have any problem because the bonds are stable. As long as the bonds are stable, you just go on forming such bonds. That's what we call catenation, self-linkage. And the element with maximum catenation is carbon. It is because of the high bond energy of carbon, which is about 80 kilocalories per mole. The C single bond, C bond energy is about 80 kilocalories per mole of the bond. So catenation is the most important property of carbon, which is making it to form millions of compounds. This number is increasing day to day because of the great research that is going on in the field of organic chemistry. Coming to the second peculiar property or the special property, it is tetravalency or quadricovalence. What do you mean by tetravalency or quadricovalence? Let me just give you details of this. The atomic number of carbon is 6. If you consider its ground state electronic configuration, it is, of course, 1s2, 2s2, 2p2. Check this out. 2s2, then 2p2. See, in ground state, there are 2 unpaired electrons. There are only 2 unpaired electrons. So this one and this one. This is, of course, a paired one. You got 2 unpaired electrons. Therefore, can form only 2 covalent bonds. Only 2 bonds. But see, when some amount of energy is supplied, you know what happens? Electron from 2s gets excited into 2p. So the excited state electronic configuration can be written as 1s2, 2s1, 2p3. Because one electron has gone from 2s into 2p. Got excited because we have supplied some amount of energy. Now look at this. It has 4 unpaired electrons. Therefore, can form 4 covalent bonds. Yes, carbon can form 4 bonds. Remember this. Carbon can form a total of 4 covalent bonds in the excited state. And the 4 covalent bonds that the carbon forms are oriented towards the four corners of a regular tetrahedron. The four valencies of carbon are oriented in a tetrahedral manner this way. Tetrahedral is what we call this. You know, the four valencies of carbon. That's what we call tetravalency or quadricovalence. Four valencies of carbon are oriented towards the four corners of a regular tetrahedron. This, of course, is the tetrahedron. Tetrahedral shape. Now, here the bond angle is 109 degrees 28 minutes. You can take any two bonds. The angle between any two bonds is 109 degrees 28 minutes. And because of the tetravalency or quadricovalency, you know, carbon can actually form four strong covalent bonds with, you know, the four bonds may be with carbon or hydrogen. These are the regular atoms that you can see in an organic compound. Or there are some heteroatoms, atoms other than carbon and hydrogen, like for example, nitrogen, sulfur, oxygen, halogen, etc. The four covalent bonds may be with carbons, hydrogen, or any of these heteroatoms. Okay, it is all because of the tetravalency or quadricovalency, which was, of course, proposed by Van 't Hoff and Lebel, for which they were awarded Nobel Prize. Now, coming to the third peculiar property, it is ability to form multiple bonds. You know, carbon can form multiple bonds. Like for example, C double bond C, C triple bond C, C double bond O, C triple bond N. See, this way it can form double or triple bonds, nothing but multiple bonds. It is because of the small size. Due to its small size. You know, only when the atoms are smaller in size, they can hold the bonded pair strongly. Otherwise, it is of no use. I mean, forming multiple bonds has got no use at all. Only when the attraction of the nucleus is more on the shared pair, it is okay even if you form multiple bonds. Otherwise, it is waste of forming the multiple bonds. Remember, only atoms with small size can form multiple bonds. With itself and with other atoms here, carbon is forming multiple bonds. With itself, double bond and triple bond. With other atoms, again double and triple bond. Even because of this property also, it is forming millions of compounds. The last one is isomerism. You know, iso means the same. Meros means parts. you can say that they are different varieties of the same molecular formula. I can tell you clearly that these are the compounds having same molecular formula. Compounds having same molecular formula but differ in their properties. Okay. Having the same molecular formula but differ in their properties are called isomers. They'll have the same molecular formula but possess different physical and chemical properties. And that phenomenon is called isomerism. Okay. So that's
Yes.
about the 4 peculiar properties of carbon. Right?
Yes.
Now,
Yes.
let us go for something about the history of carbon compounds. I'll just give you 1 or 2 points, the most important ones. Now, you know, the first and foremost theory that was proposed about organic compound was by Berzelius. Okay. You know,
Yes.
Berzelius proposed a theory called vital force theory. Vital, nothing but most important. See, according to vital force theory, organic compounds are only synthesized in plant and animal bodies. See, the organic compounds, like in our daily life also we see organic farming, organic kind of vegetables, organic fruits, organic substances. So many organic things we come across in our daily life. You know, according to Berzelius also, according to his vital force theory, organic compounds are only synthesized in plant and animal bodies under a mysterious force called vital force. By biochemical reactions only. But cannot be synthesized in laboratory. You know, they are only formed in plant and animal bodies by biochemical reactions. I hope you know that bio
Yes, sir.
means life. Only those which have got life. Yes, of course, plants and animals have life. So organic compounds are only formed in plant and animal bodies by biochemical reactions under a kind of force called vital force, which is vital and which is only present in plants and animal bodies. But what he finally told was You cannot synthesize organic compounds in laboratory. But this was disproved. Yes, of course, it was disproved by Frederick Wöhler. Wöhler was the scientist who synthesized the first organic compound, urea, in laboratory. Wöhler synthesized the first organic compound, urea, in laboratory, that too from an inorganic compound. Okay. Urea was synthesized in laboratory, disproving the vital force theory of Berzelius. It was synthesized in laboratory from an inorganic compound, ammonium cyanide. Ammonium cyanide. Let me show you that. Ammonium cyanide can be given as NH4CNO. This is ammonium cyanide. Ammonium cyanide was used to synthesize urea. This is urea. NH2, C double bond O, NH2. Urea, the first organic compound synthesized in laboratory. Very, very, very important point. From an inorganic compound, ammonium cyanide. And if you can look at the molecular formulae, see here you got 2 nitrogens, even here also you got 2 nitrogens. 4 hydrogens, 4 hydrogens. 1 carbon, 1 carbon. 1 oxygen, 1 oxygen. Both have got the same molecular formula, but only thing is there is a reshuffling of atoms. This has undergone some reshuffling in terms of atoms and gave urea. Because of that, this reaction is called, since they've got the same molecular formula, but of course one is inorganic, the other one is organic, we can call it as isomerization reaction. We can also call it rearrangement reaction. Let us now see classification of organic compound. Yes. The organic compounds are broadly classified into 2 types. They are broadly classified into acyclic compounds. Acyclic compounds, and on the other hand, cyclic compounds. Acyclic, not in cyclic form or not in the form of a ring. Cyclic, in the form of rings. So, acyclic and cyclic are the 2 major classes into which the organic compounds can be classified. Acyclic compounds are also called, because they are not cyclic, you can call them open chain compounds. Acyclic or open chain compounds, these are also called aliphatic compounds. In Greek, alephos means fats. Some of the lower members are derived from fats. So that is why these were also given the name aliphatic compound, because some of these members were derived from fats. Okay, next.
Yes.
On to the other hand, cyclic compounds are also called closed chain compounds. Closed chain compounds, or you can also call them ring chain compounds. Closed chain or ring chain compound. Okay. Now coming to further classification of the acyclic compounds. Acyclic compounds are further classified into saturated compounds and unsaturated compounds. Saturated and unsaturated. What are saturated compounds? The compounds containing single bonds between carbon atoms are called saturated compounds. Next, on the other hand, compounds containing multiple bonds, nothing but double or triple bonds between carbon atoms are called unsaturated compounds. Now, these are nothing but alkanes, or of course, the derivatives of alkane. Now, if suppose there is double bond between carbon atoms, they are called alkene. And if there are triple bonds between carbon atoms, we call them alkyne. So, alkanes are saturated, alkenes are, of course, unsaturated. Now, on to the other hand, the cyclic compounds are further classified into homocyclic or carbocyclic compounds. Homocyclic or carbocyclic. Homocyclic in the sense rings are made of only one type of atom. Homo means same. Homocyclic, or you can also call them carbocyclic, means the rings are made up of carbon atoms only. So homocyclic or carbocyclic. Next, on to the other hand, we have heterocyclic compound. When I say hetero, it is understood that the rings consist of carbon atoms along with some heteroatoms like nitrogen, sulfur, oxygen, etc. I mean, rings are made up of carbon as well as heteroatoms. Here in this case only carbon, but here carbon and heteroatoms. Now within homocyclic also we have two varieties. Alicyclic and then aromatic. Alicyclic and aromatic. Within aromatic, of course, we'll discuss all these in detail. Aromatic, within aromatic, I have benzenide type and non-benzenide type. These are the two varieties that we have in aromatic. And even in heterocyclic also, there are two varieties. The first one is heteroaliphatic, and the second one is heteroaromatic. Okay. As I said, homocyclic or carbocyclic compounds are those which consist of rings made of carbon atoms only. Only carbon atoms. Within this we have, these are of two types. The first one is alicyclic compounds. Ali, not Ali. Alicyclic compounds. These compounds consist of three or more carbon atoms in the ring. For example, look at this. If suppose I write this, don't say triangle. It is actually an organic compound. Every corner refers to a carbon atom. And see, because every carbon is forming, suppose if you take this carbon, it is forming two bonds with two carbon atoms. So let me write that in detail. C, I'm writing the equivalent figure. C, then this. This is the actual structure. But every time you have to check whether a carbon atom has formed four bonds or not. So let me just write carbon along with two more hydrogens, CH2. Even here also, CH2. And even here also, CH2. Now check out. Two bonds and two hydrogens. Yes, that is four. Means the valency of carbon is satisfied. Even here also, two bonds plus two hydrogens. Overall, anyway, it is four. Check out for this. Two bonds and two hydrogens. Overall, it is four. So that is how you have to satisfy the four valency of carbon. In this you got three carbon atoms, and that too in the form of a ring. This is what I call cyclopropane, not a triangle. So from now on, you call it cyclopropane. Check this out. This is called, of course, it can be written as CH2, 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 CH2. This is the actual structure. You know what we
Yes.
call this? It's called cyclobutane, because see, prop refers to three carbons, but refers to four carbons. As I said, ane refers to these single bonds. Even here also you got ane, which refers to single bond. Cyclobutane. Let me also give you this. This is called cyclopentane. The structure of cyclopentane can be written as Yes, no problem. H2Cr, CH2, whatever. This is called cyclopentane because it has 5 carbon atoms. Cyclopentane. Then this is, this of course is cyclohexane. Every corner contains a carbon. You just write hydrogen so that its 4 valency is satisfied. Come on. This is your cyclohexane. Like that we can write cycloheptane, cyclooctane, cyclononane. We can just go on. So these are alicyclic compounds. Now the second variety in this is aromatic. Very important.
Yes.
This word aroma has a meaning pleasant smell. See, the parent aromatic compound is benzene. In olden days, those which were having pleasant smell were called the aromatic compound. The aromatic compounds burn with a sooty flame. They burn with a sooty flame. Sooty flame because they have got too much of carbon. Soot, the black substance, what we get if suppose something is burnt on, see, a stove made of coal, where the fuel or the substance used for burning is coal. Then you get too much of soot, which sticks to the vessel, right? Soot. They burn with sooty flame since they contain more carbon percent. So these are the regular tests that were made to find aromatic compounds. Of course, the old form of identifying the organic compounds, but now compounds which are cyclic, planar, they must be cyclic, they must be planar, means all the atoms must be in the same plane. Cyclic, planar, conjugated, double bonded structures having 4n plus 2 pi electrons are said to be aromatic. This is a modern definition of aromatic compound. They must be cyclic, they must be planar, they must consist of conjugated, nothing but alternate double bonds. 4n plus 2 pi electrons, where of course n can have any number starting from 0, 1, 2, 3, and so on. Let me just give you one example. Let us take the parent aromatic compound. This is benzene. The parent aromatic compound. Yes, of course. Every corner contains a carbon. I can also give you this structure for benzene. See, the equivalent figure for this is this. Check that out. See, I'm writing hydrogens only to satisfy the 4 valency of carbon. Let me put the pi bonds also. Look at this. See, wherever you see, every carbon has got 4 bonds. Suppose if you check this one, 1, 2, and these 2 bonds, a total of 4. So every time when you write a structure, you have to check. Now these 2 are the equivalent figures. If you look at this particular compound, you know, it is a cyclic. Yes, of course, it is in the form of a ring. Planar, all the carbons, all the hydrogens, everything will be in the same plane. Next, you know the double bonds are conjugate, alternate. Yes, no, yes, alternate. Right? Like that, you just check out. Again, yes, no, yes, alternate. Yes, no, yes, alternate.
Yes.
Right? The double bonds are at conjugate position. And how about this 4n plus 2 pi electron? You know, these bonds are called pi bonds. We have got 3 pi bonds in this. You know, a bond is nothing but 2 electrons. 3 pi bonds, nothing but 3 into 2, 6 pi electrons is what it has. Now check out whether this 6 pi electron fits into 4n plus 2 or not. See, if suppose I take n as equal to 1, it will become 4 into 1 plus 2. Yes, of course, the 6 pi electrons is fitting into 4n plus 2 pi electron rule if n is taken as 1. You can just take any number and check whether the number of pi electrons what you got fits into 4n plus 2 or not. Yes, it is fitting into 4n plus 2 clearly when n is taken as 1. You take any number and see whether it fits into 4n plus 2 or not. See, here we got 6 pi electrons, and yes, it fits into 4n plus 2 pi electron rule. So therefore it is aromatic. Yes, that is how you have to check whether a compound is aromatic or not. Okay, not only this, I have many examples. Let me just give you some more. Of course, benzene is what I gave. If you consider this one, this is called naphthalene. And if you go for this, 3 fused rings. This is called anthracene. Anthracene. Even these are all aromatic in nature. If you look at the number of pi electrons in this, you know, you got 5 pi bonds, right? 10 pi electrons. Yes, it fits into 4n plus 2 pi electron rule. If n is equal to 2, then that will give you 10. Even here also, if you look at the number of pi bonds, you got 7. Isn't it? 3, 2, 2.
Yes.
Total 7 pi bonds are there. So therefore 14 pi electrons. Even this also fits into 4n plus 2 formula. So these are all aromatic. So this way we can take hundreds of examples for aromatic, non-aromatic, and anti-aromatic substances. But we will discuss all those things later under a separate heading, aromaticity. Aromatic compounds of course a part of homocyclic or carbocyclic compounds are classified into two types again. These are of two types. The first one is benzenide aromatic compound. See, as the name itself suggests, these are aromatic compounds which contain benzene ring. For example, you can take the regular benzene, next, of course, naphthalene, say this is naphthalene. Then we have anthracene. See, all these are aromatic compounds containing benzene ring. Yes, I have got benzene ring. Next, there are, of course, aromatic compounds even without benzene ring. These are called non-benzenide aromatic compounds. These do not contain benzene ring, but of course are aromatic. Let me give you examples. We have azulene. This is interesting. It is actually a 7-membered ring plus a 5-membered ring. This is azulene. It has no benzene ring, but of course is aromatic in nature. Next, we have this one also. This is called tropone. Tropone, even this also is aromatic. Similarly, we have one more thing. This is called tropolone. All these are aromatic, but see, they have got no benzene ring. Now coming to the next one, the other area is heterocyclic compound. Now, what are heterocyclic compounds? As the name itself indicates, you will have rings made of not just carbon atoms, but also heteroatoms like nitrogen, sulfur, oxygen, etc. Rings made of carbon as well as heteroatom. Okay. Now let me also tell you that these are of two types again. The first variety is heteroaromatic. Of course, heterocyclic at the same time, they are aromatic in nature. Let me just give you examples. Look at this.
Yes.
Suppose this one. This is called pyrrole. If you look at this, you have 2 here, 2 here, plus 2 here. Total 6 pi electrons are there. And you have a conjugation also. Even this is involved in delocalization. So a total of 6 pi electrons are there. So this is aromatic. Next, you also have this example. So this is called furan. Of course, you can see 2 plus 2 plus 2 plus 2, a total of 8 electrons here. But see, when an atom has more than 1 pairs of electrons, here oxygen atom has 2 pairs of electrons, but remember only 1 pair participates in delocalization. This will go here and this will of course come here. So that's how the electrons are involved in delocalization. Okay. So even
Yes.
here also, though we can see 8 pi electrons, let me tell you that we consider only one of the pairs present at oxygen atom, not the 2 pairs. So this is an interesting example.
Yes.
Aromatic. This is furan. Now you can also take, this is called thiophene. Just like furan, even here also we can see 8 electrons. But remember only one of the pairs present at sulfur is involved in delocalization. So therefore, even this also is called aromatic compound. Now, we also have one more interesting example. Say this one. It's called pyridine. Even here also, I have an interesting point. See, this will come here. This will move here. Now, whether to take this or to take this, you have two options to go for. One is the movement of this pi electron, or the other one is the movement of this lone pair. But remember, when you have a pi bond and a lone pair at conjugation, I mean both available for delocalization, remember the pi bond is involved in delocalization. So we say that there are only 6 pi electrons. Of course, including this, it is 8. But consider only 6 pi electrons which are involved in delocalization. So
Yes.
this is aromatic. Now these are called heteroaromatics. Let us go for the second variety, heteroaliphatics. Of course, heterocyclic, but not aromatic. Heterocyclic, but not aromatic. Heterocyclic means rings are made up of carbon as well as heteroatoms. Let us see that. Now, just like the pyrrole, what we have seen in the previous case, the same can be written as this without pi bonds. If you look at this, we have removed these two pi bonds. So now we can call this pyrrolidine. Pyrrolidine. Okay. Similar to furan, I have this example. So this is called tetrahydrofuran, THF. In fact, to remove these pi bonds, you have to add hydrogens at these four places. That is the reason why we call it tetrahydro derivative of the old furan. Now, this is tetrahydrofuran. Now, there is this example also. Look at this. Kind of pyridine. But no, it is not exactly pyridine. There are no pi bonds at all. Even it is not aromatic also. It is called piperidine. Just like pyridine, it is piperidine. Pyridine is aromatic, but piperidine is not aromatic. Okay, it comes under heteroaliphatic category. So that's all about the classification.